Morning, everybody. I know it feels a little bit like overkill, but we're going to continue reviewing, right, for this exam. I know some of you are feeling the, stress of this exam because it just seems like there's so many right-hand rules and things going on, but I wanted to start with this, and then I'll let you ask some questions. You get to answer all of them on Thursday. Force on a current carrying wire. Do you need a right-hand rule or not? Yes. Okay, so let's see here. All of the red asterisks means that there's going to be more than likely, I'm not guaranteeing it, but more than likely the right-hand rule is going to be involved some way, somehow, because it says force. Now, if I ask you for just the magnitude of the force, do you have to worry about the right-hand rule? No. But if I ask for the force, then you need two parts, right? You need the strength of the force, the magnitude of the force, and then you also need the direction. And you're going to find that direction using a right-hand rule. Force on moving charges in a magnetic field. Conceptual. So conceptual means there's no math usually. So do you think there's going to be a right-hand rule here? More than likely, right? Okay. So very definitely right there. Magnetic field of an arc of wire. So arcs, right? They're not full circles because we've got like rings and things like that, right? So like an arc of wire might be something like that, right? Or all the way around like 3/4 or something, right? Okay. But if I ask you for the magnitude of the field at like the center point, right, of the arc, then it's a calculation. But if I ask you for the field, what do you also have to tell me? Direction. And how are you going to get the direction? Right-hand rule. Magnetic field of a wire. So very likely it's just a straight, right? I probably should have put the word in here, straight wire, right? Right-hand rule. Yep. Magnetic field of wires, plural. Right-hand rule or not? Probably more than one, because there's wires. Faraday's law. Okay. Does Faraday's law have a right-hand rule in it? No, it has two, right? Or it can have two. But specifically, Faraday's law, like getting the voltage, the EMF, right, that's induced, that's a scalar thing, right? It's just a voltage. So Faraday's law in and of itself is a calculation. Notice that I have split out the part that's got all the directions to it, which is Lenz's law, right? Okay, so I'm pretty sure, I probably should have checked this, but I'm pretty sure the Faraday's law one does not have the right-hand rule in it, right? You're being asked to calculate, I think, the EMF, right? So probably not a right-hand rule in this one, but does Lenz's law have right-hand rules in it? It's got like all of those. It's all over the place. It's like the right-hand rules that you applied, like sometimes you have to just figure out what the external field is doing. And then you have to do another right-hand rule to figure out what Lenz's law is doing, right? Okay. All right. So if you're going to study something, what are you going to study? The right-hand rule, right? Okay. Like make sure that you, number one, use your right hand. Some of you come up to me, Mr. Bailey, you were right. I used my left hand. Yeah. So this never helped because those both look like L's to me. I have a form of dyslexia. And so spatially, I look at those and I go, oh, they're the same thing. So yeah. I remember putting a Post-it note on my hand for this exam in 4B that said, not this one. And I just wore that into the into the testing center. And they got all uppity. They're like, you can't, it's a note and all that kind of stuff. I was like, you don't understand. I have to, this is an accommodation for a learning disability. Right? And they looked at it like, okay, I guess that's okay. They thought I had notes or something on there. Not this one. Okay, so I hope that I have impressed upon your mind the importance of the right-hand rule in this exam, right? And I gave you a website to practice that on. You can give each other situations to practice it on. But let's review really quick. How many right-hand rules are there? I like to think of it as 2.5, okay? But what's one of them? When I call that a handshake, right? And the reason I call it a handshake is because there's usually a straight finger involved, no matter how you kind of do it, right? If you hold your fingers, like gun style, or you handshake like I do or whatever, right? There's always like a straight finger. So when do you use this one? Force, right? If you're looking for the force on a wire, the force on a charge, the magnetic field, because a wire experiences a force, right? If force is involved, you're doing this handshake, what I call the handshake rule, okay? And then what's the other form of right-hand rule that we have? What I call the hitchhiker, right? Where there's a twisting of the fingers. Now, you can think of the hitchhiker as two different right-hand rules if you want. This is why I call it 2.5, right? Because you can use the hitchhiker two different ways. When you have a straight wire, what does your thumb represent? The wire, right? And when you have a coil of wire or a loop of wire, what part do you use to represent the wire? The fingers, right? The other thing, the thumb or the fingers, becomes the magnetic field, right? So a straight wire makes what kind of field? A circulating field around the wire, right? But a coil of wire makes what kind of field at its center? A straight one, right? Now, that field does go out and then come back around and loop back around, but we don't worry about like the edge effects and what's going on outside. We are defining the field just at the center of the loop for that one.
Wait. Can you repeat that real quick?
Yes. For the wire, right, we take our finger and we wrap our fingers around, right? And then we have a field that circulates around the wire. For a loop of wire, we wrap our fingers around, our thumb becomes the magnetic field at the center of the loop, the direction of the field at the center of the loop. That field does extend out into space and does a bunch of things, but we don't cover that in this class. It's the field at the center of the loop that we are worried about.
And that's what we'll see most likely in Lenz's law, right?
Yes. Well, so Lenz's law, so what's the problem with Lenz's law? Problem with Lenz's law is that you typically have a loop or a piece of metal or something that's going to have eddy currents in it. And then there is a magnetic field that's coming from something else. A wire, a magnet, the aliens. I don't know what it's, sometimes it doesn't even say, right? But it just says that you have a magnetic field doing something, increasing, decreasing, pointed in or out, right? So Lenz's law is confusing on a lot of levels. One of the confusions is keeping the field separate. There's what I think of as the external field. Now, it might be totally internal, but there's some other object is creating a magnetic field that's causing the change in flux through the loop, right? The whole point of Faraday's law of electromagnetic induction is that you need a changing magnetic flux through the coil or loop where your EMF is going to be done. So something else is causing a magnetic field. Lenz's law helps us predict the direction of EMF and current in the loop, which causes another magnetic field to fight the change in flux from the original. So if I said that this field right here was decreasing, the green external field is decreasing, we have to identify two things. Number one, increasing or decreasing, and number two, direction, right? So I told you it's decreasing. Which way is it pointed? In, okay? So if we know that we have and I usually just write this down, right? Decreasing into, I don't even spell it right, okay? What is Lenz's law going to say? It always says increase, and to fight a decreasing into, we're going to increase into. Now we apply a right-hand rule with our thumb pointed which way? Why do we follow Lenz's law? The magnetic field direction. It's a loop of wire, right? So our fingers have to be the loop, and our thumb has to be the field direction. So we're going to have an into. The coil's going to make an into field, right? Into. And so my right-hand rule, hitchhiker, I don't know if that's spelled correctly, right? Tells me I go thumb into the screen, and which way is the current coiling? I had it in my head, and then I just drew it exactly backwards. Okay? So, okay, so here's the other problem with this exam. What is your explanation for the conceptual questions? Right-hand rule. It's like, okay, you can draw your hand, but like, not everybody can draw your hand or whatever. Try to be as expressive as you can on the page, right? Especially when it comes to the Lenz's law one. Did you tell me what you identified? Increasing or decreasing, into or whatever, right? And then tell me which is your Lenz's law application, and then you can say right-hand rule. Like, if some of that is correct and you miss the right-hand rule part, I can try to give you 1 out of 2, depending on how much I think you understand about what's going on, right? Right? But if all you put down is Lenz's law, right-hand rule, and you get it wrong, -2. So, like, the more you can explain what you are attempting to do or what you understand, the better off you're going to be. I know a lot of students are like, no, Mr. Balogh, I am just digging my own grave. No, show me what you know. Because when I'm sitting there grading, I'm looking for excuses to give you points. And I need excuses. Can't do anything with a blank. As long as it's right.
Or maybe not, but it's in depth.
Okay. Show me what you know. And that kind of goes to everything, everywhere, all the time. Let's see. Any other questions specifically about right-hand rules? How to apply them yet?
I don't know if it's right-hand rule question. Hall's,
Hall effect?
the Hall effect.
Yeah, we didn't really cover it. Don't worry about it. Yeah. Don't worry about it. Get Hall effect joysticks, but beyond that, don't worry about it. Okay. What are your questions? Last minute things that you just have to know, figure out.
I think we should do like a big review, just like a general review since
It's just been too long. Let's do a general review. Let's just follow the topics.
Yeah, why don't we just like put the equations we're gonna need?
I mean, I've done that for all the stuff prior to spring break. Okay, so you help me. Force on a current carrying wire in a magnetic. Okay, let's. Can I copy this? I can copy this. Copy. All right. All right. Force on a current carrying wire in a magnetic field. Let's. What possible equations could we need for that? There's I remember that one. There was, there was a variant that was like, I had an L prime on it. I don't know if you remember that. Like, if you have like a magnetic field and you have a wire that's like going places in the magnetic field and you knew like where it started and where it ended, then what's L prime? It's just the straight line distance between the 2 points, right? But regardless, right, if it's force on a current carrying wire in a magnetic field, it's going to be that.
So like, okay. So we're given, like, what would be given, like IJK?
Oh, well, yeah, it could be that, right? It could be do a cross product. It could be, because this will become ILB sine theta, and if the current and the magnetic field are at 90 degrees to each other, it's 1. Sine of 90 is 1.
Oh yeah, you're right.
Yeah, okay. Like, variations on a theme are a very big thing in physics and engineering. So like, could ask you to find the force if you know the current and the magnetic field and length of the wire. Or give you the force and the current, what's the strength of the magnetic field, right? Like there's different ways to ask this question about exactly the same topic, right? So how would you find the magnetic field if you knew the force and the length? You'd solve for B. Now that's kind of a nightmare if you've got this big cross product, but if you can do ILB sine theta, like you know the angle between those two things, then solve for B is much easier. So lots of different ways to ask the question or to probe your understanding of this cross product relationship, the force on a wire. Does anybody else remember anything else there? I have my notes in front of me and I don't. That's motional EMF, and I would have called that out down in the chapter 30 stuff. It would have been on there. I would have told you. Yeah, I would have told you. This is the Lorentz force. That's one part of the Lorentz force. QE. Oh, you mean QV cross B?
Yeah.
So that's the next part, force on moving charges in magnetic fields, right? Okay. So one last thing, okay, for this one. What is the force? What is the net force on a loop of wire in a magnetic field? 0, right? Closed loops have 0 net force. They do have net torque, but the force is equal to 0 on a loop of wire. Okay. Force on moving charges in a magnetic field. So mathematically, this is QV cross B. Conceptually, what do moving charges do in a magnetic field? They circulate or deflect, right? They're moving along arced paths or in circular paths. Whether it's an arc or a circle depends on the strength of the magnetic field, the mass of the charge, all the different kinds of stuff. But the point is that they are deflected, right? And they're deflected into like a circular motion, be it an arc or a full circle. And so conceptually, like, what could I ask you here? Yeah, so like, well, not how much force, because that would be like a number, right?
Is there a force?
But is there a force if it's deflected? Yes, there's a force. That's too easy. That's too easy, right? Yeah, I'll take that question, right? Okay. But obviously, it's going to involve right-hand rule because it's like conceptual. It's the idea of what's going on here, right? So I mean, I guess, what do you write down for equations? I mean, that's kind of it right there, but that doesn't help you with the concept. So what do you put down for like on your cheat sheet? I don't know. Give me a magnetic field in or out of the page. Out? I heard out first. Okay. So here's a magnetic field. Clockwise or counterclockwise arc? Clockwise arc. So a charge comes in, enters the field, and curves like this. So this is like the path that the particle takes, okay? Positive or negative charge? How do you know?
Wait. That's a charge going through a field?
That's a charge going through a field, right? The green is where the magnetic field is. And we know the path of the charge. You made this one up, right? I just asked for directions and you.
Do we know what charge it is?
I'm asking, what is it, positive or negative?
We want to know which side is positive, which is negative to determine the charge?
Nope.
Is it negative because when you do the right hand roll?
Okay, so this is a right-hand rule problem, right? QV cross B. What do we do? This one or this one? It's a handshake. It's a force. We're talking about forces, right? Does this particle experience a force? Yes. How do you know? It deflected. Okay. Which way was the force?
To the left. I don't. Forgot the
The force was that way. How do I know the force was that way?
Wait. Out, in, left.
It's curving that way, right? It feels a force in the direction that it's being pushed, right? Or pulled. And it's being pulled towards the left. Okay? All right. So, and that force will be perpendicular to the direction it's traveling. The velocity is changing along that arc. Okay. So, we start with our velocity at the top of this picture, right? I get my fingers out, and my velocity has to be going kind of down into the magnetic field, right? It enters from the, do you see the black arrow? Maybe you don't see the black arrow. Black arrow, right? You guys pick the directions, not me. Okay? So it's entering into the field, right? Kind of at an angle, and then it's going to be sort of turning as it goes, right? Which way is the magnetic field pointed? Out. So now I've got to rotate. You guys picked the hard one. Okay? So my finger is out. It's going down and kind of curving around as it goes, right? Like that. Which way is my thumb pointed? Towards the center of the turn, right? Positive or negative charge? Positive. Because it follows the right-hand rule.
Use my left hand. Damn it. I did the left hand again.
So let's say it arcs like this.
No, like, show us your hands.
I just did. Okay, from doing it this way, never turn your back to the audience. I don't know where that rule came from. Theater. Okay, so V is coming down, and I'll eliminate all my other fingers now, right? V is going to kind of do this, right? It's golly, physics 4A. When it didn't curve that way. Curve the other way. Okay? The V's tangential at every point. right? Yeah. So your finger is going to follow all of those V's. Now, at every point, the magnetic field is perpendicular. Right? It's pointing out no matter how I hold, no matter what direction my V goes, my finger still points out of the board, right? Which way is my thumb pointing? Always towards the center of the loop. Follows the right-hand rule. Right-hand rule is defined as positive.
If it follows it, then it's positive. That's the other way. It's left-hand rule if it's negative.
Yeah.
Negative is left-hand rule. We're trying to help.
Okay. Class dismissed. I give up. No. All right. The right-hand rule gives you the direction of the force that a positive charge experiences. All of these definitions, like from day one, for electric field, right? For charges, all these, it's voltage. It's always been from the point of view of a positive charge, right? And then the exceptions to the rules are negative charges. Negative charges will roll uphill. They'll go the other way. They'll do, right? Okay? So if you apply a right-hand rule, knowing the velocity, we know the velocity, and we know the magnetic field, and we know the force, right? All three things have been given to us. So does my force line up in the correct direction? Yes. Is my field lined up in the correct direction? Yes. Are my fingers lined up in the correct direction? Yes. This must be a positive charge. It has to be. It's following the right-hand rules, following the definition.
Oh, okay. So like it was curved the other way.
So now with the blue one, with the blue curve over here, right? Now, my V, so my finger's still going to stick out of the board, right? I haven't changed the direction of the magnetic field. My V, though, is going around the other way, right? Is my thumb pointing in the correct direction for this force? No. What do we know? It's a negative charge, because your negative charge you flip over. Or go ahead and say it. Okay? I don't like the left-hand rule because students sit there going, which one do I use? Always use a right-hand rule, and then when it doesn't work, it's a negative charge. How do we know that electrons are negative?
Benjamin Franklin.
Okay, Ben Franklin didn't know about electrons. Electrons were 1896. Okay, Ben Franklin was like 1750 something. Okay, so Ben Franklin didn't know about electrons. He picked wrong for what charge was which. Like, was it the cat or the rubber rod? Right, but that then set the charge of the electron later when J.J. Thomson would discover it. So, how do we know electrons are negative? Because they bend the wrong way in a magnetic field. No. We are wrong in our Ben Franklin was wrong. It's Ben Franklin's fault. Okay, so force on a moving charge in a magnetic field, conceptual. You could be asked to identify, like we did here, the sign of the charge. You could be asked, which way will a electron circulate in a field? Right? What direction is the magnetic field if the force and circulation are like this for a positive? Like there's lots of different ways to ask the question, right? But they're all the same skill that is being tested, right? So, oh boy, we're doing good. Magnetic field of an arc of wire. So we kind of, I mean, I drew the picture over here, but there's an equation for this one somewhere. What did I do with it? Right there. Magnetic field for an arc of wire is mu naught I all over 4 pi. I used big R for some reason, theta. Okay, couple of caveats here, right? Theta, like the amount of angle of the arc, whatever it is, right? And it would be like from, like theta would be all the way around there, right? So how do I put the angle into this equation? It must be in radians, okay? Don't put it in degrees, right? If it says that the arc is, I don't know, 70 degrees or something, change that into radians, yes.
I noticed there would be an issue sometimes in homework where you would do like the theta of the outside angle, like the
Uh-huh.
one they give you is the opposite angle. When do we do that?
I mean,
'Cause,
this angle and this angle are the same angle.
no, it would be like the interior version of that angle, but they give us the exterior. Or,
Oh, well, like they might give you this. They're just trying to be tricky.
yeah, good enough by having to use.
Yeah, you have to use the full amount of arc.
When do I? Because I would basically just do like back and forth on if I had to do an angle. Like I couldn't tell when I had to do the full angle or just that interior part.
I have a little.
I'm not sure I understand. I mean, I understand your question, but I don't understand the context.
I'm just saying, like, when do I know which angle is which? You know what I mean?
It's contextual. For this equation, it's the full amount of arc.
You have to go counterclockwise from the x-axis. So you have to go counterclockwise.
It doesn't matter.
Yeah, but when they're like asking like frames of references, that's usually the way they go.
Oh, well, that's a Wiley plus issue, but
Yeah.
in terms of this angle right here, it's the amount of arc that you have. Total amount of arc.
Just get both angles.
I think it is just like a Wiley thing.
I think it's got to be a Wiley thing. Yeah. Because the answer doesn't change. Let's see, can I do this?
Like, was it
Nope.
not accepting a certain thing?
Yeah, like it wouldn't accept the angle. I would do everything.
Yeah, that's a Wiley thing.
If I use the other data, then it works. I'm like,
Should be the same answer.
It keeps pasting the whole thing. Darn it.
X-axis restriction.
So it doesn't matter if so let's say I do 90 degrees of arc. So like that, right? Okay. This is 90 degrees. The answer does not change if you do that 90 degrees of arc. It's exactly the same. For the magnetic field at that dot. The amount is the same. And as a matter of fact, the directions, if the current's flowing the same direction, the direction's the same. Now, there were like conceptual questions where there was like, there's the one that went like this and then like this, and then the one that went like, no, and then it went like that, right? And then there was like, it did a big, and then it did a small, and then it did the big one, or something like that, right? What do you do like to find the total? Like if I want the magnetic field right there, what do? You have that arc, and then you have this arc, and you add them. Why am I doing that in quotes? Because the direction of the magnetic field matters, right? So right-hand rule, all that kind of stuff.
wait a minute, how would right hand look into that one?
So let's say the current's flowing this way.
And which right hand would
Yeah, which right-hand rule do you use?
the one with
Hitchhiker, why? There's no force. It's just a magnetic field, right? And it's a magnetic field of an arc. So to do this top part of the arc right here, which way do I wrap my fingers? Around, going around, right? In the direction, yeah, okay. And so which way is my finger pointing now? It's pointing out. So the top half has an outie.
Wait, why was it turned that way?
I just chose it that way.
So we'll be given the turn?
Yeah. And then what about the smaller arc? It's in, right? Now, will it have a different magnitude? But the angle's the same amount. But the r, remember the equation has an r in it, right? The radius is smaller. Okay? So you would have to take the difference between those two calculations to get the correct answer, right?
Subtraction?
Yes. Why? Because the directions are opposite. Yeah, they're fighting each other. Whereas this one, they're going in the same direction. No. Top loop. Which way is my thumb point? Out, right? Bottom arc. Which way is my thumb pointing? Same direction. The straight line segments don't do anything, right? Yeah, I didn't like it either when I was in your seat. Magnetic field of a wire. What's the equation there? Do I have that? Right here. Mu naught I over 2 pi. And I wrote this as A. That's a Mr. Baloghism. To me, I see very little difference between those two equations. Like, I don't see the 2 or the 4 as being different is the problem with my brain, right? But I do see an A being different than an R.
What is the A?
It's still the distance from the wire. Your book will write R, right? But I just need a different symbol to trick my brain into realizing that this is a different case. It's a different situation, right? This is the infinite straight wire equation. But that's a trick I do to keep it straight in my head. You don't have to do it that way. Keep your R's straight. You're probably smarter than I am in keeping your R's straight. Magnetic field of wires. Well, we just kind of did all that right now. Right? So, same difference. So I would have said magnetic field of a ring. Okay? Because that was the other one that we did. This awful thing right here. But yeah, no. You can have the loop down on there if you want. I don't think you'll need it. No, I'm hitting the wrong button here. You know, 2 pi a. There we go. The one for the loop was mu naught I over 2r. Which again.
What about the one with cosine theta 1 minus cosine theta 2?
That was the result, the generalized result from Biot-Savart law, which simplified down to this for the infinite wire. So no.
So it's going to be like an infinite.
Yeah, it'll be an infinite wire. Whew, how are we doing here? Hope this is helping. I'm a little bit worried about your guys' reaction to that one. All right, Faraday's law.
Wait, what's the right hand rule for this? For the magnetic?
There's no force. Faraday's law. The negative sign, this is always a struggle, and it's because You guys have been taught that negative signs mean something. Well, that they mean literally what they say, and they don't in physics. The negative sign is a reminder of what? Lenz's law. Okay? That's what it is. The negative sign there says the EMF will always go in a direction that counters the change in flux, right? So it's a reminder of Lenz's law. When you're calculating the EMF, do you need the minus sign? No. I always wrote it with absolute value signs on both sides of the equations, right? Positive or negative, go use Lenz's law to figure out the direction. If you're just calculating the EMF, just find the change in flux. What's the N doing out there on the front? It's, the number of turns, right, in your thing. So this brings up flux, right? And what is flux? It can be that nasty integral, but don't worry about the nasty integral. Yeah, it's BA cosine of theta. Because in almost every case, except that chapter, number 9 that I gave you, the flux simplifies to this. That horrible integral can collapse to this for this level, of course, right? If we were in senior level, we'd be doing, but actually wouldn't use integrals either. So the key thing, because we're finding a change in flux, right? Change in time, one of these needs to be changing. Minimum. I guess you can have a couple things, but at least one of them is going to change, right? So you and the problem again can be different. The area could change. The size of the loop, the strength of the magnetic field, the way that the loop is oriented with respect to the magnetic, right? So you got to identify what's changing. Most often in the problems you got, it was like a magnetic field that was changing, right? And like you had a homework problem, I think, where there was like a wire that had a current in it, that the current changed or something, but they ended up telling you how the magnetic field changed anyway, so you didn't need the current. So problems can try to trick you. I don't go out of my way to trick you, but I do borrow problems from other test banks and books and stuff, and sometimes I don't catch the trick because I see beyond the tricks, right? And I don't realize that it could mess you up. So do realize sometimes information in a problem is extra, not needed, that kind of thing. But yeah, find what's changing. Usually the magnetic field. Spoiler alert, we're really going to cover this part of the change in the next unit. So I wouldn't worry too much about cosine thetas, right? It's either the B or the A for now. Yeah, and then if I gave you a voltage, could you find the magnetic field it started with? Yeah, if you know the initial, you can find the final, right? Can you solve for the number of turns in a loop if you know the voltage and how the flux changed? Yeah, that was your lab that you did, right? Had you solved for the number of turns in that coil? Because the computer gave us what turned out to be the flux, right? So change in flux. So yeah, there's lots of ways to ask you to calculate that equation. Figuring out the parts comes down to, well, which of these things is changing, right? The magnetic field is the area, is the angle. And then Lenz's law, conceptual. What I had long ago, I think I had all of this. I had increasing into, increasing out, decreasing into, decreasing out. Oh, as a matter of fact, I remember this teacher didn't let us have cheat sheets. And so I had a cheat sheet and I had to memorize this and write it down as fast as I could. So this, one of these is, right, the flux, the change in flux. The other side will be Lenz's law. The response, right? And what's the response to increasing out? This was easy because it was all increasing, wasn't it? And so increasing into, I would increase. Increasing out, I would increase. Decrease into. Decrease out. Right? And I just kind of had that matrix, if you will, that table kind of in my head. I sat down and I just wrote it down on the back of the exam before I even looked at any of the questions. And with that, right, which of these two, blue or red, do you apply the right-hand rule to? It's the blue one, right? The second step part. But I often didn't write down like my steps. Yeah.
Should be for the decreasing out should be increasing out.
Yes. See? Messed it up already. I guess it's too long ago. I probably messed it up when I wrote it down on the test, and that's why I didn't do very well on it.
Wait, what?
Hmm?
Wait, you messed up how you write on the test?
Probably. I was constantly in my teacher's office. They're like, why did you write this down when you drew it this way? And I'm like, because I'm an idiot. And they were like, but you're not an idiot, so why did you do it? And so so after my halfway through my junior year, that's when one of my teachers like, have you been tested for learning disability? So, yeah. Well, no, because he's like, you know this stuff, you can explain it, but then you write it down backwards. Like you write exactly the opposite thing. I am. Well, I have a type of dyslexia that's not I don't have like, dyslexic people like sometimes see words backwards and definitely write words backwards. And I do write words backwards a lot, especially vowels. Get really switched up in my brain. And for the life of me, my computer, I think, is just about to burn out its processor on this one. Every time I type the word the.
Oh, you put though?
T-E-H. And it just has to autocorrect.
Sounds like
Doesn't matter. For some reason in typing, it's become te. Maybe it just be meh. But yeah, I hate writing.
It's a motor disconnect.
Yeah, it's So dyslexia is a family of motor problems. Motor is brain to output. So it can be speaking, it can be writing, it can be handwriting, it can be expression of ideas. It's obvious to me, maybe it's not obvious to you, I have no struggle when it comes to verbalization. Like I can verbalize pretty well. You will often see me write one thing and verbalize it differently though, right? I said the right thing and then wrote the opposite. That's my Achilles heel. That's why my handwriting is really bad. Yeah. I read really fast. Like really fast. And classic dyslexia, they have a really hard time reading. I don't have that problem. I can make information go into my brain really fast. Dyscalculus? A lot of people have dyscalculus.
I have a friend who has it. He's a math major.
Yeah.
He's a math major. And he's a stats tutor.
All right. Other questions? Yes.
Are we going to have to deal with any integrals?
Are we going to have to deal with any integrals? I would have called it out.
So not even set up for like the first one, because I know.
So like Bio Savar and all that kind of, I'm not making you start, like you're not deriving anything.
This one, we don't need that, right? That's just,
So that is ILB cross B, right?
okay. arrows, the
Yeah,
line squiggly
and then
line
if
that
it's a
you want.
squiggle, you don't do the integral, you just do the straight line distance
Okay,
between
don't
the 2
worry,
points. Yeah, yeah. So you're not setting up integrals. You're using the results of many integrals, but
I just remember something that I'm confused about. Remember that you multiplied the dt over to the EMF to get
Yeah.
something related to flux?
Yeah.
What was that about again?
now you're asking me a math question.
For what?
Multiply both sides by dt. Okay. What's this? Change in flux. What's this? Change in flux. There's an equal sign right there.
You divide. It's voltage times.
This should not be. This should not be
Volts times second.
reinventing your universe.
That's flux.
What's this?
Voltage.
Voltage. What's this? Voltage. Why is it voltage? Because there's an equal sign right there.
There was? I couldn't tell.
What's this? It's a change in flux. What's this? A change in flux over time.
So what we could do is we multiply
That I hate to break it to you this late in your career. That's what an equal sign means. Means they're the same.
Wait, say that again.
Actually, it doesn't mean that it's the same. When you said F equals MA, that means it's proportional.
Yeah. Yeah. Related to. But the units on one side have to be the units on the other. Now, MA is not a force. It has units of force. Yeah. This EMF has units of voltage, and so does this have units of voltage. Yes. No, proportional to, strictly, we have a different sign for that. It's the fishy symbol. Did I answer your question?
Yeah.
Okay.
I never thought an equal sign meant that.
No, like, no. You see like flux without like time. I thought it was.
Yeah, no, you guys see it differently, don't you? You see this as being different from this, and I don't blame you. Why do you see it differently? Different symbol. And you've been taught that a ddt is a derivative, and so that has to be a totally different thing. It's not. It's a different way of getting at the same thing. So, yes.
Can we do number 2 on chapter
28, number 2.
It's the one with like a d is greater than or less than the ratio.
Oh, God. Okay. I've done this problem so many times. No, it's good. It's good. No, it worked. Glory be. See, I went, and got made fun of. The rest of you went, and there was empathy and sympathy. I know.
You did this to us.
I know. It was for your own good. Yeah, it was for your own good. Where am I going? I'm going here. Oh, this takes so long. Okay.
I think it's just that they're like deciding on the E and B ratio.
Yeah, it is, right? And okay, so let's ignore the ratio thing for right now. Just ignore the ratio thing for right now. It only comes into play in a certain case. Okay? Looking at particle 1. Okay? So what we are doing is we are applying the whole enchilada, the entire Lorentz force law. 2 parts, right? Yes. Force on moving charges in magnetic fields. Sure. We did. Oh, good luck, Lewis. What? Yes. We just did it. We did a bunch of it. Well, okay. I apologize. I think I understand what you're saying. We did this part of it. Was your question add this into it? Sure. But the stuff in the circle you should know already. No, that's fair. That was fair. That was definitely fair. Where would you know QE from? Chapter 22. Okay? So that should be in the bag. Okay. But I'm pretty sure I focused only on this for the test. So to your question, yeah, I don't think you need to worry about this as much. But in this problem you do, because there's an electric field right there. Which way is it pointed? It's kind of hard to see. It's pointed into, right? We have a magnetic field pointed to is that the right left? I can't remember anymore. Okay, so for particle number 1, which way would the force be on it because of the electric field? It's a positive charge. What do positive charges do? They follow the electric field. Okay? So the force from this is into the page, right? How do we find the direction of the force on charge number 1 from the magnetic field? This is where we do the right-hand rule, okay? So which right-hand rule is it? It's the handshake, because we're dealing with a force. They're asking us for force. V straight up. Magnetic fields to the left. My thumb is pointed which way? Out. Okay. Yeah. What's that? Out. Typically that's the case if X is to the right and Y is up. Because then you have a right-handed coordinate system. All right. So this one is now out, right? For charge for number 1. Okay. So we're left with not knowing which of these forces is bigger. Is it QE or is it QVB, right? And that's where the speed column comes in. But we're going to come back to that. Let's keep going. Charge number 2. Where's charge? It's also going up. Okay, but it's still a positive charge, right? So these stay the same, right? The charge number 2 was going up just like charge number 1. They're both positive. Okay. Charge number 3. Here's charge number 3. 3 is over there. It's going down now. And it's a positive charge, so it's going down. So what happens with the electric field? It's also into positive charge. It's going to follow the electric field. But now, if it's going down, so V is down, my magnetic field is to the left. Which way is my thumb pointed? Into. So it doesn't matter for charge number 3 that I know greater or less than that magic speed, because they're both pointed into. So what direction is it going to go? Into. It's just going to go into. Okay. So for number 4, where's 4? 4 is right here. It's just like 3. It's a positive charge. We just did that. All right. 5. Oh, okay, what's going on with 5 here? 5's going down, but it's a negative charge, right? So what does that mean for the electric field? Out. Ooh. You know what? We'll do it in blue. Out, because it's a negative charge, right? And then what is our right-hand rule going to tell us? 5 is going down. My field is to the left still. My thumb is pointed into the page, but it's a negative charge, so I flip my answer. So it's pointing out. Now, since both of them are pointing out, which way is this charge going to go? 6. 6 is negative going down. It's out again, isn't it? It's no different from charge 5 as far as those two force directions are concerned. 7. Back to positive. What's 7 doing? Oh, okay. So 7, 8, 9, and 10. What's the B? 0. Because the magnetic field direction and the velocity direction are aligned. It's either 0 degrees or 180 degrees, but it doesn't matter. Sine of 0 or 180 is 0. So now it's only the electric field that's going to determine the direction, right? So positive would be, and negative would be. Okay. So of all of these cases, the only two that I have to worry about this greater than less than thing are numbers 1 and 2. And the reason I have to worry about it is because I have an opposition. The electric field and magnetic forces are opposite each other, and I need to know which one's stronger, right? So they give us this information about V, right, being equal or greater than or less than this magic ratio, right? What I like to think of it as is which of these two wins, right? If V is small, if this speed isn't going very fast, what does that mean for this term right here? It's going to be small, and so therefore this term will win. The electric force doesn't depend on the velocity, does it? Okay. What if V is really big? Then it wins, right? So when it says less, they're trying to tell you that this side loses. But if they say greater, then what does this do? It wins, right? So we had to identify all the ones that would come towards you or out. So which ones come out at us? 9 and 10. 5 and 6, and then it looks like number 2. Because number 1, with the speed being less, means the electric field is going to win. The electric field's pointing into, so it's going to go into. It's more important that you understand the first two things than the speed greater than or less than, because I'm not going to ask you questions about that.
Real quick, if you did look at 9 and 10, if we are doing E over P, can't you like not divide by 0?
The magnetic force is 0. The V is not 0. But the magnetic force, this cross product, V cross B, is VB sine theta. And what's the angle between B? What's the angle between number 10 and the magnetic field? 0. B and number 10 are both pointed that way.
Oh, so it's 0 plus, it's not.
Yeah. You're not dividing by 0. You're adding these two together. And I know your brains like reject anything that's not a number. If I'd put like positive 10 and negative 4 on these columns, you would have been right with me. You guys don't, the abstraction of is it bigger or smaller than people have trouble with.
I'm not sure if you answered this already, but will we have an integral on this test?
MS, that question, the answer is no. Not like directly. All the equations that we developed from integration.
Okay.
And we've developed them, so we don't need to develop any more of them. I'm not a big fan of asking you like derivation questions. Sometimes you have to derive, like all of the electric field stuff we kind of had to derive on the fly.
Yeah.
But with the magnetic fields, there's only so many cases we can do, and we did all the cases. So that's why 4A is kind of really difficult, that second unit, because you're deriving stuff from Newton's second law for every problem.
What's the next level of this class? Like, what would they take away and make it harder?
No, it's not what you take away to make it harder, it's what you put back in. So we would start doing all of the not infinite wires, not infinite solenoids. And so you have to find the vector fields in their entirety. So you need a mathematical expression for the electric or magnetic field everywhere in space. What we are doing is we say, okay, the solenoid's infinitely long, which means we only need to know the magnetic field inside of it, which is uniform and constant everywhere. Okay? When it's a not infinite solenoid, now the magnetic field comes out, curves around, right? Forms closed loops, and you have to solve for equations everywhere. And it turns out there's one. And you can find the one equation that represents the field everywhere, but you need a different kind of math to do it. Yeah. It is. It's really, actually, it's amazingly powerful. It's really cool. Vector calculus. Tensor calculus. Tensors are just another word for matrices. It's just the matrix is full of operators as opposed to numbers. Okay, have you guys studied operators? Function operators? Like, you've done the upside down delta.
Oh.
That's an operator. I can't do that math anymore. I think I can read it. Like if I look at it long enough, I'll be able to figure out what it's doing and what it's saying. I couldn't generate it without practice. Right. Yeah, no, there's no way. It's been 28 years since I did problems like that. Yeah. My specialty is very much the first 2 years now. And I tell people this. I don't consider myself a physicist anymore. I consider myself an expert in teaching physics to first and second year students. I also consider myself an expert in 18 to 27-year-olds and how they learn physics. So. Well, then I don't know what you're doing. No, the oldest student I've ever had was in his 70s. I will see you on Thursday for the exam. You're going to remember which hand is your right hand. You're welcome. You put in the request, and when I finally get it in, probably tomorrow, you'll be just fine. What time did you schedule it? Okay, perfect. Has that been working out better for you? That's been working out better for you? I knew it would.
And also, like, yeah, I already like studied everything, so we'll see how it goes.
So is it this Friday that you get to hear from UCLA? Did you really? Oh my goodness.
So if I don't get in, I have to practice. Yeah, I'll keep you posted.
Berkeley's a crazy place.
Berkeley?
Berkeley. That's what I call it. I've been there a couple times.
It seems very competitive.
Yeah, getting into Berkeley's tough.
Yeah, no, being there is even harder.
Yes. UCLA is the same though.
That's true. But
No, it really
I
is.
think it's a better suit for me.
Well, probably. I know it's where you want to go.
So I'll definitely keep you posted.
Okay.
It's exciting.
But Berkeley's a good backup. Yeah. You're welcome.